way by companies with a range of different interests, creating an infrastructural reality that runs counter to the common imagination of the global internet as a distributed mesh able to easily circumvent any attack in a specific geographic region and route traffic around any disruption. This chapter argues that in order to understand the geography of signal traffic, we must move beyond network topology, the observation of the geometric or mathematical distribution of nodes and links, to consider network topography, the way that infrastructures are embedded into existing natural and cultural environments. Paying attention to network topography counters several widespread assumptions about the determinants of cable routing. First, there is a terrestrial assumption. People believe that undersea cables are used only when a terrestrial cable route is not available. Researcher Linda Main argues that since running cables over land is less expensive, undersea cables have traditionally been used only between continental land masses, where terrestrial links are not feasible. Cables are assumed to follow the shortest geographic route between continents in order to minimize underwater segments. When cables do not land at the closest terrestrial points between land masses, their geography is often explained by an urban logic that assumes that cables directly connect the centers of major cities, reflecting a broader focus on the city as the critical unit of analysis for telecommunications infrastructure. A third assumption is that cable routes are driven by demand. They are extended to places where there is a surplus of signals and not enough cables to carry them. This is an anthropocentric and equalizing view of the cablescape. We assume that, like people, cables must be easier to sustain in accessible and central environments and are simply extended to users who lack connection. This chapter shows that even though terrestrial, urban, or demand-driven logics may at times play a role in determining cable routes, our global infrastructure has been constructed in relation to historically specific social and environmental imaginations. Security, in the broadest sense, has always played a critical role. Companies route cables in ways that insulate them from potential interference in their surrounding environments, ranging from natural disasters to anticipated geopolitical friction. Counter to any presumed terrestrial logic, a secured network has most often been an underwater one. Territorial politics have made laying routes on land incredibly difficult. Douglas Cunningham of Arctic Fiber argues that the ocean and its ice will serve as a layer of insulation. He commented in one presentation that 60% of cable breaks are from ship anchors and trawls, and observed that this route will actually be safer than the other routes because we have, on 34% of the length, ice cover for 7 months of the year, and that is protection. The deep sea has been the safest zone for a cable because it is farthest from people, and subsea engineering is more reliable than terrestrial engineering. Components function for decades underwater. The closer a cable gets to shore, the more heavily armored it must be. Although it is true that many cables do connect urban centers, which remain significant endpoints for data flow, landing points are rarely established in the heart of cities. Rural and suburban environments, like the ocean, protect cables from the potential turbulence of human traffic in densely populated areas. The Arctic Fiber cable, though described as going from London to Tokyo, actually lands far outside these cities. Complete insulation of a cable network is never entirely possible or profitable. Such insulation would make it impossible for cables to interconnect with the sources of traffic necessary for operation: other undersea cables, domestic fiber optic systems, and rail, road, and air transport networks. As Stephen Graham and Simon Marvin argue, for this reason new infrastructures are often layered over existing transport and resource systems and rarely develop in isolation. Cables have often been laid to locations where there is already enough capacity as a way of generating competition, stimulating increased signal traffic.